Recently, we've been talking about linear functions. These are functions that obey t of alpha times x equals alpha t of x, and t x plus y equals t of x plus t of y. The domain of this function is going to be Rn. The codomain is going to be Rm. We have recently figured out that we can always represent such a thing as t of x equals a matrix A times x. Each x in the input space gives a single A times x in the output space. Since these are linear combinations of the columns of A, we know that the range of t must be the span of the columns of A. All of the columns of A are column vectors within Rm, but an issue is it all of Rm, or could it happen that there is a B which is not the target of any A times x? If each y in Rm is equal to some value t of x for at least one x in Rn, then we say that the function is surjective, or onto Rm. For example, I might have my linear function be the matrix of all ones multiplied by vector x. I forgot to write the vector x in. This maps vectors from R3 into R3, but is it onto? Given a vector in the codomain, y, is it true or false that no matter how I pick that y, there's an x to go with it, so that t evaluated at x gives me that y? The answer to this is either yes or no. So let's look into this. Select a vector in R3 over in the codomain and try to solve the system of equations t of x equals y, writing out the coefficient matrix and the y's. Then we do the row reduction in the usual way, and we see there's going to be a problem here. The bottom equation says 0 equals y3 minus y1. The next equation up says 0 is y2 minus y1. If y2 minus y1 is not 0, then there's no solution. Likewise for y3 minus y1. The only way you're going to get a solution is if all three components of y are equal to each other. This function is not onto. As an example, 777 is in the range of the function because you can easily solve the system of equations involved. You can easily see that by letting x1 equal 1, x2 equal 1, and x3 equal 5, that the a times x that goes with it is in fact 777. Let's do the same for the vector 102. I want to see if that's in the range of this t function. If I set up the same system of equations as before, I find out that I'm out of luck. The last two equations can't be satisfied by any value of x3. This provides a verification that this function is not onto because we've actually found a y, which is not a times x, no matter what x is. The second type of functions that we want to look at are called one-to-one functions, also known as injections. It's a direct observation, then, that t is 1-to-1 exactly when the only solution to a times z equals 0 is for z to be 0. As an example of this sort of thing, let's let the matrix be the 3 by 2 matrix with numbers 1, 2, 3, 4, 5, 6. I'd like to figure out if this is 1 to 1 or not. We've got to look at 1, 2, 3, 4, 5, 6 times z1, z2 equals the 0 vector. Write out the equations as usual, and you will find out that z2 and z1 both have to be 0. The only solution to a times z equals 0 is z equals 0. This tells me that this function is 1 to 1. Another example, I'll have the matrix be the 2 by 3 matrix, 1, 2, 3 across the top row, 4, 5, 6 across the bottom, and investigate what kind of solutions I can get to matrix times vector equals 0. It turns out that anything that looks like a number alpha, another number negative 2 times that alpha, and then alpha again will work. If I pick alpha to be 1, write out my matrix times vector, I end up with the 0 vector as expected. If I let alpha equals 2, the same thing happens. This tells me that this function is not 1 to 1. Coming soon, Introduction to Matrix Algebra. In the meantime, I hope everyone's having a good day, and I'll talk to you again soon.